So I will start this discussion with basic terminology. We have already covered this actually, but let's have a quick review. For example, the earthquake rupture or slip initiate at a certain point underneath the surface. We call that point as hypocenter or focus, right? The point exactly above the hypocenter or focus on the surface is called epicenter, right? The earthquake intensity or shaking experienced at that point is called epicenter intensity. This is the fault plane, right? This is the plane of that slip or plane of that rupture actually. If it is recorded at a particular site, maybe this one, the distance directly from the hypocenter to that site will be hypocentral distance, right? And the distance from epicenter to that particular site will be epicentral distance. So both of these distances are actually sometimes referred to as the source to site distance, right? Source to site. Depending upon what you are referring to when you say source, sometimes epicentral distance is reported, sometimes hypocentral distance, right? Actually, hypocentral distance is more representative of the actual source to site distance, because the actual source originated at a particular point called focus or hypocenter. The depth of focus from the surface is called hypocentral depth. Sometimes it is also referred to as the seismogenic depth or simply the depth of an earthquake, right? So depending upon different depth ranges, we also classify earthquakes as shallow earthquakes, intermediate earthquakes and deep earthquakes. Generally, earthquakes having a depth less than 33 kilometer or in some references less than 50 kilometer, we refer to that earthquake as a shallow earthquake, right? And from 33 to maybe 100 or 150 is intermediate and more than 150 is deep, right? And then we also have very deep earthquakes like which originate at a depth of maybe more than 200 kilometers. So many of the large magnitude earthquake in the Hindu Kush region, which we also sometime experience here in Islamabad, they are very deep earthquakes. So Hindu Kush region is continuously producing large magnitude deep earthquakes. So magnitude may be 7 or 6.5, but the depth is more than 200 kilometer. Even in that case, the shaking experienced by the different sites or residents may be very small, right? Because it is a very deep earthquake. So the word intensity and magnitude I'll explain later. They sometimes refer to as same, but actually there is a difference. Both of them actually tell us about the size of an earthquake, intensity and magnitude, but the intensity is actually dependent on the distance between the recording station or wherever it is experienced and the source. But magnitude is not dependent on the source to site distance. Magnitude is a constant number which will be just defining that earthquake, and at all locations and distances magnitude will not change, right? It will be same thing, but intensity will be changed. So today's topic, first topic is the seismic waves and their measurement, right? So I'll quickly skip through this discussion because mostly it is covered in many other places. So seismic waves are actually the elastic waves or energy carried by those waves, disturbance in the medium actually, which is soil or earth's crust in this case. They may form many complex patterns, these disturbances or waves, when they pass from one type of medium to another type of medium. They can be reflected or refracted also. So for example, here you are seeing this is a very famous Loma Prieta earthquake. It originated from this point. So almost immediately they reach to the epicenter. The very first point where they will reach to epicenter is directly above that. and then from there they also reflect back from the surface. They also penetrate within the body of earth, and depending upon different soil layers, they can be refracted also, depending upon the density of different layers of earth, right. So whenever they pass from one type of medium to another, for example, base of crust is 25 kilometer and below that is mantle, which have a different density. So they are refracted. Actually part of it is refracted and part of it is reflected back, right. So if they are experienced, for example, at another city, if I record that earthquake at another location, the seismic waves which I am recording, they reach me from different mediums, right. So they have a different signature in them. There can be some part of that wave which directly reach me, right. Some can go to surface and then reach, some can have many reflections and finally reach me, right. So actually the signal which you will be recording at another location will be very complex, right. It will not be a simple movement, it will be random motion which is having many frequencies coming from reflecting and refracting from different medium or type of soil layers, right. So the actual pattern, if you can trace, will be very complex, very difficult to understand. Some waves can go into the body of earth and they may dissipate their energy, right. So we classify them into three basic types: primary, secondary and surface. Primary and secondary are sometimes also called as body waves, and surface waves are the ones which first go to surface and then reach to our recording station through surface, right. P waves are compressional, right. They are like sound waves, alternatively push and pull. They push and pull the rock and they spread in this manner. So they are like sound waves, initial shock of the rupture. So they can travel through both liquid and solid. So they can travel through the liquid rocks also, right. S waves are shear waves, they are transverse waves, and the definition of transverse wave is that the movement of medium is perpendicular to the direction of propagation of wave. In compressional waves, the movement of medium is along the direction of propagation of wave. So it moves the rocks or whatever is the body of medium sideways at right angle to the direction of travel. They cannot propagate in liquid parts of the earth. So which means that from oceans or from magma, liquid rocks, they cannot pass. So they just, this liquid will just simply cut their path, right. So this is an illustration which you can also find on various websites and learning resources, that compressional wave actually will disturb the material in this manner, that some part of it will compress, some will expand, then that compression will travel along the direction of propagation of wave, right. But transverse waves or secondary waves are like this, they will move the material of medium in perpendicular direction. So some part up, some part down, and this movement will continue when the wave will pass. The second type is surface waves. These two are body waves. Surface wave actually again have two types, Rayleigh waves and Love waves. They have a different, both of them are surface, but they have a different movement of their medium. Rayleigh waves are rolling waves. So medium actually moves in this rolling manner, right. So disturbance travels in this rolling manner. But Love waves actually move the material in sideways. So some part on left, some part on right, some part on left and again right, right. So both travel on the surface, but they move the medium in different directions. So actually we can say that we have 4 types in this slide. So this illustration also is showing how the S wave is moving a particle of a medium and how a P wave is moving. So you can see here that any dot on the medium, which is this red dot for example, in P wave it is moving to and fro in the direction of the propagation of wave, but it is moving up and down perpendicular to the direction of a wave in S wave. P wave is the fastest, after that is S wave, and the surface wave are slower than both P and S, right. So, which means that if you record at a particular site an earthquake, you may have this kind of a horizontal acceleration graph. Let us say UG dot dot is my ground acceleration, horizontal ground acceleration in one particular direction, let us say east direction, for example, east west. So, in that case we may have a graph like this, that there will be no acceleration, and suddenly when P wave will arrive, the reading will start, and then after some time you may have an S wave arrival, and after that even you may have surface waves, right. So, you may clearly identify in most of the cases when is the P arrival, when is the S arrival, when is the surface wave also reach and they start participating in the movement, right. So, I will skip all that detail. I think that introduction for both of these types is enough. So, this is how a typical recorded ground displacement or acceleration graph may look like. P arrival, and after that S arrival, right, and then finally maybe surface at the towards the end. The time difference between P and S arrivals is an important parameter, this time separation, right, and this will give us an idea about how far we are from the seismic source, right. So, this will be more if we are very far, it will be small if we are close to the seismic source. We can simply derive actually an expression which will give us the distance from our site to the source of that earthquake if we are given with this T. For example, let us say that this time separation is represented as delta T, and delta T is actually what? T2 minus T1. Let us say T2 is the time from which the S arrives, right, and T1 is the time at which the P wave arrived. Let us say I start recording the earthquake from this T, let us say this is T equal to 0, and at T1 I have P arrival, and at T2 I have S arrival. So, T2 minus T1 will be simply my delta T, right. So, I can simply use an expression, distance is equal to velocity is equal to distance over time, which means that distance is equal to velocity into time, and T will be simply S over V, right. So, both S and P wave originate from the same source. So, the distance for both S wave and P wave is same. The difference is in their velocities, which will be converted into difference in their time arrival times using this simple expression, right. So, you can simply write that T2 is equal to S over V2 and T1 is equal to S over V1. Both will have same distance S, because they originate from the same source and they reach to this point. So, the distance for both the cases is same, but the velocities for both cases is different, right. So, if we put this T1 and T2 in this expression, and we know the velocities of both S and P wave, which we can estimate and we already have a very good idea about, right. So, given the velocities of S and P waves, generally the P wave have a velocity of 6 km per second and S wave have around 3 to 4 km per second, but we have more accurate estimates also, but this is a rough range, right. So, we already know their velocities, right, and distance can be calculated if delta T is known. Let us say delta T is 2 seconds in our case, we can put that in expression and S can be worked out, right. So, by just having a recorded acceleration history, I can tell that how far it actually that earthquake occurred, right. So, for example, on a map, if I have an earthquake which originated from here, let us say this is the epicenter, right. So, I have a recording station here at this point, a recording station here and a recording station here. I can estimate 3 different S values, this one, let me call it S1, this is S2 and this is S3, right. So, if I just make a circle for this S1, I can actually tell from one time history that whatever is the seismic source, it is located on that circle, right. If I have another distance, I can make another circle, maybe like this one, and I can identify two potential points at which the seismic source can occur, right? And then if I have the third one, I can exactly pinpoint, right? So that's how we can quickly locate the epicenter, right? We just need at least three recording histories. So different international organizations have set up the detailed seismic monitoring networks in different areas. They have real-time monitoring of earthquakes. So as soon as an earthquake occurs, we have many recordings available, and from each recording we can work out the distance from source to site, and we can have these three circles to exactly locate the epicenter. If we have more than three, then we can be more you can say exact about the location of epicenter. So this acceleration is not the acceleration of wave, it is the acceleration of that earth point on earth's surface which is recorded by a station. So we have a theory of acoustics already available which give us a very clear idea about what will be the velocity of a particular wave in a particular material. So we have even closed form expressions available for an elastic homogeneous material. If the density is available and elastic modulus is available, we can work out the velocity of a wave which is traveling in that medium. So this expression is telling us that as we are more away from the hypocentral distance, for the same earthquake, the distance between P arrival and S arrival, the time separation will increase, right? So the same earthquake was recorded at this station, and then this station, and all those stations have a different distance from the source, right? So if you plot the distance from the source on the y-axis and their recording histories on the x-axis, so you can exactly see that at a particular time, for example 5 seconds, the P arrived at Kobe, but it didn't arrive at Osaka. At around 10 seconds, P arrived at Osaka, and then in the 15th or 20th second it arrived at this location and this location, right? So these kind of you can say visualizations where you have the seismic source to site distance on y-axis and the arrival of different types of waves on x-axis give us an idea. Similarly, you can see here that the distance between S and P arrival is also increasing as you are going more and more away from the source, right? So these curves, if you join all P arrival points and S arrival points, they are called distance time curves or distance time relationship. So red line is a distance time relationship for P wave. Blue line is a distance time relationship or distance time curve for S wave, right? Our mathematical theory says that this relationship should always be linear. As you go away from the source, this separation of time should be linear because we are using a linear expression to estimate that. But in real cases, these are curves. When you go to around more than 200 kilometer away from the source, and then you record things, these are actually curves and they are called distance time curves, right? So I give you one quick assignment, also a kind of a reading assignment, to please check why this relation should be in a curved line, why it shouldn't be always linear, right? So this is same thing I just explained, that how we can quickly estimate the delta or distance from source to site if we are given with TSP, which is the separation of P and S arrivals. All we need to know is TSP from a given recording and the velocity values for S and P waves, right? Yes. So same thing, we need at least 3 recordings in order to locate the epicenter. Obviously these are elastic waves, so they follow the law of sines and the reflection and reflection laws, right? So whatever law of waves we have for elastic waves, these seismic waves also follow the same law. This is an example where the distance from source to site is on y-axis and the recording values from the same earthquake is on x-axis. So at different recording stations at different locations actually recorded the same earthquake, but they lie at different distances from the source. So these are all the recording stations and corresponding readings which they recorded, right. So you can see that that peak value of ground acceleration, it is you can see a pattern like this, that it is reaching in different times at different locations, right. And also you can see the reflection back, maybe at around 200 kilometer from the source to site, there is a very hard or stiff you can say strata or some body of element or something which is causing those seismic waves to reflect back. So some part of it is reflecting back. So you can see that reflection again in the same recording values, and some small peaks here which are represented as R2 here. And then from here again a series of reflection, then again, so R3, R4. Although with each reflection their amplitude is reducing, but the phenomena itself can be clearly visible if you have this much detailed data recorded from the same earthquake, right. For shallow earthquakes we may assume that epicenter is the source, but for deep earthquakes obviously from that expression itself, that distance is equal to velocity into time, the distance ideally is the hypocentral distance, but for shallow earthquakes we may assume that epicenter is the source itself, right.